the machine learning models we're building are models that can generally rearrange atoms. They understand how to rearrange atoms in almost any way that you want. The potential for that is enormous, right? Look at the impact on the human race that arranging silicon in 2 dimensions has had, the enormous computer revolution. What if you can arrange more than silicon in more than 2 dimensions? That's what we're trying to build.
Hi, folks. I'm Conor Gaughan, and welcome to Consensus in Conversation, a podcast where we're talking to the innovators, entrepreneurs, and thought leaders who are committed to building successful businesses that also help us build a better world. I've got a fun question to start us off this week. If you could pick any piece of sci-fi technology from any book, movie, or TV show and make it real, which would you choose? It's a lot of fun to debate this question, as long as you don't pick a time machine. But there's also a point. Quite a few real-world technology advances have been inspired by science fiction. Simon Lake, inventor of the submarine, and Igor Sikorsky, inventor of the helicopter, both got the idea for their machine from Jules Verne's novels. Leo Szilard, who patented the first nuclear reactor with Enrico Fermi, became aware of the potential and also the danger of atomic power from H.G. Wells' book, The World Set Free. Martin Cooper, the head of R&D at Motorola during the development of the cell phone, didn't just get the idea of wireless communications from Star Trek, he even took the flip phone design straight from the show's props. Unsurprisingly, it's Star Trek that continues to be one of the leading inspirations for innovators of our own day. And so it's also from Star Trek that I'll pull my wishlist technology, the replicator. Now, confession here, I'm only a casual Star Trek fan, like very casual. And I had to get my producer to remind me what this machine is actually called. But I do remember that even amid the warp devices and holodecks and teleporters, it always stood out to me as one of the most intriguing ideas on the show. For those who are a bit rusty on their Star Trek, the replicator is the machine that can create anything out of anything, just by converting matter and energy in the environment. Mostly they use it to make food on board the ship. Tell the replicator anything you want to eat, and boom, 1 second later, you've got your cheeseburger. Think about the potential impact of replicator technology. Imagine a world where you could synthesize anything you needed at any time without needing any real raw material inputs. Not just how convenient and awesome it would be to, say, never need to cook dinner again, but how much that capability would change society on a fundamental level. I mean, for one thing, if everyone can make meals out of thin air, do we even need agriculture anymore? How much human energy and talent could be freed to pursue new things if there was no need to grow or buy food? Now apply that to every industry. What becomes possible when we're able to transcend the laws of supply and demand? This all leads to the idea of a post-scarcity society. And much like the warp devices and teleporters, I had assumed that it was one of the most fiction-y of science fiction ideas. A beautiful one, to be sure, but one that's further beyond the horizon than even the most speculative research on nuclear fusion or quantum computing. I had assumed that until my conversation with today's guest. Now, I'll let you in on a little something here. We'd initially planned on going an entirely different direction with our introduction. My producers and I had originally intended to talk about the challenging issues surrounding lithium mining in the U.S., the importance of lithium to building a decarbonized future weighed against the environmental impact of expanded mining operations. It's an important conversation and one worth having, and it is part of today's story. But that dimension of what my guest today was doing was only the tip of the iceberg. We were so completely blown away once we began to understand the potential of his technology, if it proves to be scalable the way he believes that it will be, that science fiction was generally the only basis of comparison that we could think of. Because my guest today is on a mission to build the technology that leads to precisely the kind of post-scarcity world imagined in works like Star Trek. Pavle Jeremic is the founder and CEO of Aether Biomachines, a deep tech startup focused on, well, you know what? I'm going to let him explain it to you. Let's jump right in, and I'll see you on the other side.
Aether is a protein engineering company, and what we do specifically is we take these little nanoscale machines, proteins, we use our robotic laboratory and our machine learning algorithms to engineer a protein to basically do whatever we want at the nanoscale. So that could be grabbing onto certain metals so we can mine them like titanium or lithium, or it could be rearranging atoms so we create an entirely new class of polymer for a new type of ballistic armor. But it's basically saying, hey, I want to rearrange atoms, almost like Tinker Toys. And I say, this is the new arrangement of atoms I want. And our system figures out what's the protein nanomachine that's going to make that rearrangement of atoms happen.
Wow. Okay. I really want to get into unpacking exactly what all this means, but let's actually back up quickly. Where I want to start is at the beginning. I kind of want to hear a little bit about where you're from, where you were brought up. Yeah, just tell us a little about yourself.
I had a pretty unusual childhood growing up. So my parents fled Yugoslavia when the Civil War broke out in the early 90s. They came to the United States to do their PhDs. I was born while they were graduate students, which I can't even imagine having a kid as a graduate student. And of course, being graduate students, they weren't paid a lot, which same thing's true today. So they couldn't really afford daycare. And so when I was growing up, part of the year I'd be raised either in the US or whatever country it was that month or that year in former Yugoslavia, either by my parents or my grandparents. And so I sort of had this dichotomy when I was very, very young of one part of my life was in the United States in university towns, which are very nice. And then the other world I was in was a world that was sometimes an active war zone and was a country that was collapsing while I was there. So that left a lifelong impression on me that not every part of the world is calm and nice and as wonderful as parts of the United States. And it left an obsession with trying to understand where does that discrepancy come from and what can I do to try to resolve that discrepancy?
I mean, it really becomes part of your whole ethos the rest of your life. Yeah.
Yeah, exactly.
And I have to imagine, I can't imagine, but I have to believe that those kinds of experiences have to shape an individual in profound ways. I mean, I also know you spent a lot of that time in the university setting, in the graduate school setting, in another unusual way, which is growing up in labs, growing up with academic parents. Was science always something that you were passionate about?
Always.
Yeah,
I think that's the other part. Exactly. Both my parents are academics, civil and electrical engineering. And so when I was here in the US, I was being taken care of in their laboratories. And so There was this very unusual experience of being surrounded by technology. And so I think one, that made me obsessed with technology from as long as I can remember. But also, I think one huge benefit was I was never intimidated by the academic setting or anything like that. I was able to reach out to professors as a middle schooler or a high schooler and ask questions. It was just the world that I grew up in.
Yeah. It fueled intellectual curiosity, that kind of, by the time you're in high school, you're already doing some crazy, intense scientific stuff.
Yeah, I was really fortunate. I had a professor at UC Davis, Mark Facchiotti, just took me in and let me do my own synthetic biology research. I'm internally grateful to him. It's kind of what led me to where I am today. And by the time I entered undergrad, I already had like 4 years of experience doing real laboratory research.
I want to hear about what is it like to be a high school student doing real lab research? Let's even back up. What is synthetic biology?
Let's start there. So synthetic biology is just the latest kind of nom de jour of genetic engineering. So it's trying to take fundamental building blocks that living systems are made of, usually pieces of DNA or protein, and trying to figure out how to change them, modify them, splice, reinsert, just change them in ways to have an outcome that we really care about. Like, can I get this bacteria to produce a biofuel? Or can I get this plant to produce a medicine? Or can I get the microbe to react to the environment in a way that I want it to? And so genetic engineering or synthetic biology is a relatively nascent field. It's changed enormously since even I started. And we're in a world now where we are able to very rapidly rewrite the genetic instructions for many different living organisms and try to create new types of technology based off of that. So it's just engineering life is what synthetic biology is.
So rewind to 2010, 2011, 2012, when you're in high school, beginning to kind of think about this. How did you realize this is something you were passionate about or wanted to pursue or wanted to study? What was it a class that you were exposed to? Was it a question that you were presented? How did it come about that you in high school become interested in this?
So it actually started before high school. I had been thinking for a very long time about how do I have this kind of impact on the human race? How do I create a future of abundance for the human race where a lot of the desperation that led to a lot of the wars in the world doesn't exist anymore? I had read a book that was hugely influential on me called Engines of Creation by Eric Drexler. It's basically the first serious treatise on nanotechnology after Feynman's talk about it back in the 80s or I guess late 70s. I read this book, and that book convinced me that I needed to build a future with real nanotechnology, to build really complex products anywhere on the planet at super low cost, whether it's a life-saving pharmaceutical or a phone. But I couldn't figure out how to build real nanotechnology. I wasn't sure how to do that until I was very fortunate. I had a class in high school. It was a biotechnology class. And that class is actually how I got connected to the professor at UC Davis. And through my research at UC Davis, I realized, well, biology has created something that kind of looks like nanotechnology. It's not the eventual solution, but it's the closest thing I found. And so through this biotech class, I was introduced to the world of synthetic biology. And I realized that synthetic biology was the starting point, the jumping off point to actually build real nanotech. And then we were off to the races from there.
Yeah. And as you evolve and continue in education, you choose UC Santa Cruz. I'm curious kind of what was the calculus there?
Yeah. Well, I mean, I got rejected from a bunch of colleges, so that's part of it. I would just skip class and just go to the lab all the time. I didn't really care about school. But one thing that stood out in UC Santa Cruz, there were two things. One, it was very close to Silicon Valley. That always was important to me because I had a strong suspicion that the best way for me to have this impact on the world was through a startup, at least to begin with. The other thing was when I toured UC Santa Cruz, I found that there was an enormous amount of resources for students that were just not being utilized. I mean, I remember when I was working at UC Davis or when I'd go to visit a lab at UC Berkeley, we had to run some experiments there. The competition for resources for undergrads was fierce. I mean, I had a leg up because I was a high school student. So I didn't even have to go through the undergrad process to get some of these resources at UC Davis. I was able to skip the line because I wasn't even technically categorized. So I already knew that if I wanted to start doing research immediately, it was going to be harder at a place like UC Berkeley. And at UC Santa Cruz, there were all these labs set up for students. Like I walked by this one lab when I was being given the tour and it was empty. And I was like, what is this lab? And they said, well, it's a student lab. And I said, well, why is it empty? And they said, well, no one's using it yet. And I was like, okay, this is right by Silicon Valley and there's no competition for resources. So I'm going to come in here and I'm just going to have whatever I need to do to build whatever I need to do. So I think those were two really significant things that convinced me UC Santa Cruz is the right place to go.
Fighting banana slugs for the win. It's around this time that you, I think, started the iGEM project.
Exactly.
So tell us a little bit about that, because it sounds like that could become part of the fundamental framework that then that evolves or that you kind of use to continue.
Exactly. So basically the narrative arc here is when I was doing research in high school, I had already become convinced of two things. One was I felt like a robot all the time in the lab. I mean, I can't tell you how many times I was there till like 1 a.m. just moving liquids back and forth and like checking off boxes in my lab notebook to run experiments. And I was already like, a robot should be doing this. So that was kind of the most obvious realization. The second realization I had towards the end of my high school experience was that these nanoscale protein-based machines are very, very difficult to engineer. They don't really behave like macroscale machines. And it became more and more clear that machine learning would have to be the solution, that humans would not have a good intuition to engineer these, but we could build algorithms that could engineer them for us. And there was a company at the time called Transcriptic. It was called a cloud laboratory. So basically you would send them samples and their robots would run experiments for you. So towards the end of high school, I was actually considering dropping out and doing a startup where I was going to say, I'm going to use Transcriptic to run my experiments for me, and I'm just going to build models. When I entered undergrad, there were 3 experiences that led to the foundation of Aether. I did some research in a molecular biology lab. I gained a lot of experience, and I pretty much at that point confirmed I wanted to do applied research. I wanted to build stuff. That was like my deepest foray into pure science, which I wasn't interested in. I did research in astrophysics, and I did a lot of computational modeling in that space. And that's where I realized, well, hey, I'm actually not bad at this. And then iGEM was an opportunity to say, well, I've never really run a team before. I've always been solo in the lab, just doing stuff and talking to the PI once a week. So I really saw it as that opportunity. And I knew a lot about iGEM because the professor that mentored me at UC Davis also runs the UC Davis iGEM team. So I was very familiar with what it was. And I thought to myself, well, I would like to run the UC Santa Cruz iGEM team. For
folks that don't know what it is, give us a kind of a 2-second on what iGEM is.
iGEM is a really amazing competition. It stands for International Genetically Engineered Machine. I highly recommend it if you're interested in synthetic biology. It is an international genetic engineering competition. And so basically what it is it is a global competition. There are now, I think there might be 1,000 teams now. And each team comes up with a project idea on their own, a synthetic biology idea, and they try to execute on it over the course of I think it's 3 months or something like that over the summer and the fall. And then they all meet up in one place, the Jamboree, which is a huge kind of conference/competition. They compete. And then you see who wins, who got the best project that year.
What was your project? Or do you remember the winning project? How did that kind of become formative for you?
I was trying to think about this before this call. I don't remember the winning project that year, but our project was, I had a bunch of different ideas of what we could do. And I wanted to try to create a project that could potentially turn into a startup. And so what the project was is basically engineering this microbe to take waste products from agriculture in the Central Valley here in California. So mostly almond husks, which there's a crazy amount of that's just totally wasted bio stuff, and convert it into a 0-calorie sweetener, erythritol, and do so at low cost. Now, we succeeded in the individual parts of the project. We didn't actually create the full machine to do it because, it's only 3 months. But we were successful, and it was an amazing project. We did not actually pursue this as a startup. And I'm actually glad we didn't. Erythritol is incredibly cheap to manufacture. Now that I've gained a lot of scar tissue from running a startup for a while, I know it would have been a terrible idea. So I'm glad we didn't. But yeah, I can't recommend iGEM enough. I think it's an incredible opportunity for people.
Yeah, it sounds like it. And you were self-aware enough going into that to think leadership was something you wanted to explore and experience as a pathway towards the startup world. Do you remember when the entrepreneurial bug bit you, like when you started to think about, maybe it's not just a lab I want to do, I want to be in the lab setting, but I want to build a company? When did that experience?
I actually remember when that experience happened. So when I was very young, I was trying to think, how do I have this impact on the world? And it struck me that there were basically two ways to have real impact on the world. There was the political route, and then there was the sort of corporate economic route. I was not convinced of the political route to begin with. The problem with the political route on its own was it struck me that we did not yet have the technology to build this future of abundance. And it doesn't matter how effective your policies are. If the technology doesn't exist, the policies aren't going to do anything.
Sure.
So it's sort of, well, you can do a lot in a sort of capitalist private economy world. If you run a company, there's a lot of impact that you can have very, very quickly. I don't know that necessarily the idea was startup to begin with, because I don't know that I knew what a startup was necessarily.
Yeah.
But those were the two paths. And I pretty much eliminated the political route as the starting path. So I said, well, the other route has to be the path that I take. So how do I get there as quickly as possible?
I want to talk a lot more about that notion of how a company can be, harnessed for good in a bit. Now I think it's the time to actually just dig in on Aether and the company itself. So give us the origin story. Where did this idea come from?
So the genesis of the idea for Aether, I was convinced in high school already of high throughput automated experimentation using machine learning. And so like a lot of the core ideas were already there. And then I think what happened in undergrad was, as I was doing more and more computational work, a concept became very clear to me, which was the way machine learning, if I oversimplify, works at its core is you have a data point and you have a label, right? You have an image of a cat, and then there's a little piece of text that says cat, right? Or something like that. And that's how at least supervised machine learning works. You have to have labels. And I was thinking about this from the perspective of engineering proteins. And I was thinking about the fact that proteins can actually do a lot of different things. Like people 30 years ago used to think that like enzymes, for example, did only one thing. Evolution had selected for them to do one chemical reaction and that's it. And it turns out that's just not true. Like they do a lot of other stuff that's totally unknown to us right now because we just haven't found them yet. And I was thinking about this from the perspective of machine learning. And so like I was thinking, well, if you have a data point, which is your protein, and you have a label for it, and it's only one function, it's not all the 300 functions this protein can do. Well, your machine learning is never going to be able to engineer anything novel. You've incompletely labeled your data set. Your model doesn't actually understand what this protein is, it just understands one dimension of what it can do.
Sure.
And that really became a core concept for Aether when we were thinking, well, if we were to really build the data set that would let us engineer proteins to do almost anything, we would have to create data sets where we don't test every protein against one or two functionalities at a time. We'd want to build a system that could test these proteins against many, many different targets in parallel and see what are all the different things these proteins can do, and then feed that to our machine learning model. So we call that indexing. That's kind of the term that we've come up with. As far as I can tell, we're the only people on the planet that do it. And there's sort of two advantages to this approach. One is, if you just ignore the machine learning component for a second, we accidentally discover new types of chemical reactions all the time. I mean, it's astonishing the degree to which natural and unnatural proteins just do stuff that you're like, I didn't even know that was possible, but cool. So there's a lot of stuff already, if you just ignore the ML part, where it's like you could build companies off of some of the data only we know is possible. But then when you layer on machine learning on top of it, this data doesn't exist anywhere else on the planet. And what really is happening at Aether is the machine learning models we're building, and we have built, are models that can generally rearrange atoms. That's what they can do. They understand how to rearrange atoms in almost any way that you want. The potential for that is enormous, right? If I kind of get a little grandiose for a second, look at the impact on the human race that arranging silicon in 2 dimensions has had, right? The enormous computer revolution. Yeah. What if you can arrange more than silicon in more than 2 dimensions, right? What happens to the potential for the human race? What kind of products or capabilities can we create 20 years from now that are unimaginable today? Because 20 years from now, we have machines that can just arrange stuff at the nanoscale for us in whatever shape or pattern that we want. That's really what we're doing. Fundamentally, that's at least what we're trying to build. And then we build products off that. So we do a lot of work in kind of lithium mining, some defense work as well. We'll talk about that later.
I want to hone in on something you just said. I think it's really important. You're looking 20 years downrange. And, I think thinking about and building and innovating and investing in such a long scale, maybe abnormally long for most folks in the venture capital space, the growth capital space, it's a long time horizon. How does that operationally manifest? Like, how do you build a business plan or a team or a company culture or an investment deck that talks about 20, 30 years into the future?
Yeah, it's a good question. So, I mean, a couple things. Certainly, the path to here has not been straight, right? There's been a lot of things that have gone wrong, things that have gone right. So there's scar tissue and lessons learned along the way to this point. And I'm sure there's a lot more scar tissue to come, just hopefully new scar tissue. That's kind of the goal. So I think it's important to not overthink the 20-year plan, but to think what are the key capabilities you want to keep generally building towards, right? So that's the way I think about it. So for example, when we think about our mining programs, the reason why we're doing the mining programs is because, one, we think we can build a product and generate substantial high margin revenue over the next 2 to 5 years. That's kind of obviously part one. But part two is that when you think about that long-term vision of building a future of abundance, when we're designing our metal extraction systems, what we're seeing and we're designing towards is that almost the same system that mines lithium is going to be the same system that mines titanium or that mines vanadium or manganese or whatever else. And so even though today I have not yet designed my titanium extraction system, we are very intentionally building towards a more generalized capability than just mining lithium ourselves. So that's kind of how it manifests is you want to avoid putting the cart before the horse, right? You do not want to design all the systems before you even deployed the first one. Because actually, I would say that that's the biggest lesson that I've learned is learning cycles are so much more important than I possibly could have realized. You set a direction, you say, I want generalized metal extraction systems. And then you say, okay, what is the metal that we can learn on the fastest, that we can get the most funding for, that we can generate the most revenue off of? And just push on that, learn our lessons on that one, and then we'll design the next one based off those lessons rather than trying to figure out everything right off the bat. Just start iterating, just start shipping as fast as you humanly can.
Yeah. And I mean, you gave one great example on the mining front. Give us a couple of the other kind of ways that you think about product lines or categories. How are you kind of divvying up the world of opportunity? Because it feels almost infinite to me listening to you talk.
Yes. I mean, that really is, I think, one of the key challenges for Aether is there's so many things we could do. I mean, we had pilot programs where we engineered DNA modifying enzymes, everything from enzymes that can strip CO2 from flue gas and potentially make it cost effective to enzymes that would degrade the molecules that make body odor, right? So I think one of the key challenges that Aether has is how do you say no to most things? Because you can't possibly do everything. And so I have an idea of what the next category of product is going to be, but we're not quite there yet. But I'll tell you kind of how we came to the conclusion of what our current 2 products are and how we kind of thought about that. So mining, it made sense because it's aligned with the mission of future of abundance. I mean, imagine a world where titanium is as cheap as steel, right? The potential is enormous. And there's this huge synergy in all future products where the learnings from how we build our modular lithium miners are going to apply to the third metal we pick. And so when we go to market on the third metal, it's going to be 5 times faster, 5 times cheap. It's a flywheel that we're trying to push to start right now. Materials is our other area of interest. So why materials? Well, on the material side, there was sort of 2 reasons why we picked it. The first is that when you think about the potential of these sort of nanoscale protein catalysts, protein machines, enzymes, pick your term, it's not just the simple chemistries. Like, can I add a fluorine onto this? Or can I add a nitrogen onto this? Or remove a nitrogen? What if we can engineer them to make structures at the nanoscale, right? Because if we really start to think about, I said at the beginning of this conversation that biology was, even though it looked like nanotechnology, it is not the final version of that solution. Well, what I meant by that is that biology evolved to solve a very different set of problems than what the human race needs to solve. And so the only way that I can get beyond this limitation is to start building real structures at the nanoscale so I can start to build components of nanoscale machines. So the materials work, the genesis of it was, how do I start to build something more complex than a single molecule? How do I start to build cages at the nanoscale or containers so that I can start to build more complex systems? And then what we also realized when we thought about the go-to-market was, we're not making existing materials. That's a low margin, very difficult to break into business unless you have something unique that I haven't seen yet. But what we were realizing was there was a lot of these materials, and especially additives for these materials, new classes of polymers that you can blend with other materials, where no one had ever been able to make these chemically. They've been theorized about since the 70s, but no one had ever been able to make them. And we were looking at this and thinking, well, the point of the mining program is to vertically integrate in manufacturing. Because we're not going to be making batteries 2 years from now, maybe 20 years from now, but we're not vertically integrating in that direction. But we do want to vertically integrate in the supply chain side with mining because that's where we see the synergy. The opposite is true in the material space. the properties that we're able to create now, programmable properties, like properties that can change depending on whether you've hit the material or heated or exposed to radiation, these are pretty significant changes to properties. We can massively strengthen a material under certain temperature regimes. There's a lot of potential both for industry, but also for defense. And so to begin with, we're just selling powder and saying, well, we will sell a powder to someone else. They'll blend it into their existing product and their product just gets better. But the goal is to start vertically integrating in the product direction, to start saying, okay, 2 years from now, Aether is actually making composite fiber that people just integrate in their product. 5 years from now, we're making armor plates that people just slap onto something, or components for jet engines or something like that. That's those two strategies. What I like about them is they are sufficiently orthogonal from each other that we are de-risking different things about the long-term potential of Aether, and we're not taking the same risk at the same time in both. Sure. So there's sort of this nice complement. But the other fascinating thing about this is, which I didn't even fully appreciate, but it's been happening a lot, there's an enormous amount of synergy on the scientific side between the two programs. So, for example, the nanoscale proteins that extract metals, the way we manufacture those now is the technique we use to manufacture some of the materials. It just turned out that when you're making something more complex than a little string or a little blob of a molecule, and you're making more complex structures, the world of chemistry kind of unites to the same types of conditions and the same types of reactors. So there's synergy that I just totally did not expect between these two programs. That's been quite helpful, actually.
That's awesome. I want to pause and ask a different question. Just listening to you describe the products and the way you think about them. You know, we had a great conversation a couple of weeks ago with a capital allocator in the clean tech space who emphasized how important it is for startups to capture their ethos of storytelling, being able to tell the story. And it strikes me like when you think about the scientific and technological complexity of what you do, it's really important for you to be able to tell the story. You know, I'm already picturing like how my mom will interpret this whole episode, right? Like, you know. Yeah. So tell me about that. Like, what have you learned in the process of fundraising, of communications with, you know, folks that aren't going to have PhDs in the engineering, scientific, or technological fields about not just how you tell your story, but just the importance of being able to do it?
Yeah, I think there's definitely been a ton of lessons learned there, right? I think one of the things that's important is trying to pull to tangible examples as quickly as possible. The problem I had early on was kind of like something you said earlier, you know, there's so many potential applications of this technology. I think early on when I was telling the story of Aether, I was kind of blinded by all the potential applications. And so my narrative and my pitch would be exciting but vague, because it would be like, yeah, I can rearrange atoms. So, you know, the world's my oyster. But that isn't helpful when you're trying to educate someone who has never thought about this before. Because right, like, I don't think a lot of people think very much about the fact that literally everything that we are and that we touch and we interact with and the whole history of our lives and the history of our species is made from little patterns of atoms. So I think even something as fundamental as that constant understanding, because people don't think about it, if I just say I can rearrange atoms programmatically, it doesn't click immediately. Like, why would that be so impactful? So I've always found it helpful to go to very specific, tangible examples, like with mining, and say, hey, this is a little machine. It floats around. It's like a mousetrap, and it just grabs onto lithium and pulls it out for us. And I'm going to be able to do that for any metal. And you're going to see super environmentally friendly, low-cost mining happen anywhere. And every metal is going to be, $1 a pound or something. And you're going to see, if titanium is as cheap as steel, you're going to see skyscrapers that are miles tall at that point. Like, that's what's going to start happening. So I try to pull it to the kind of macro scale applications and the tangible output of that. Like on the material side, one of the examples that I found to be super helpful, like our main product in the material side right now is actually a product that makes a plastic that everyone wants to use manufacturable, because this plastic has a lot of really good properties, but it's almost impossible to melt. And, that's kind of a problem, because that's how we make things out of plastic, is we melt them into the shape we want. So our additive actually makes this material more meltable and it strengthens on the back end. That's an okay example, but it's still kind of abstract and a little vague. But in theory, this additive should also allow for materials to heal themselves. So you can start the tangible example that I think is a lot more legible to people is say, well, imagine a plate of armor that after it's impacted, after a couple hours is fully healed and is ready to operate again. And you just have planes or tanks or soldiers where they're as safe as they can be because their armor is literally healing every time it's impacted by something else. Trying to tie to those applications that are as understandable as possible. I think that's really, really key.
It makes me think about another question, which is at the very fundamental level, how would you, if pressed, identify your industry? Would you consider yourself a biotech company, a hardware company, a mining company, a material science company, right? Like you're all of the above. Where do you land on that when asked?
So I don't consider us a biotech company for two reasons. One, because that term tends to refer to pharma.
Yeah.
Just in general, it tends to confuse people. But two, so I have a pretty strong point of view on this, and not a lot of people like this point of view. I think that most applications of biotechnology are a really bad idea. And what I mean by this specifically is, I mentioned earlier that nature evolved to solve a very different set of problems than what the human race needs to solve. Sometimes they overlap, right? It turns out yew trees make an anti-cancer drug, right? Like, by coincidence, nature solved the problem for us. But it hasn't solved every problem for us. And more fundamentally, when you look at how biological systems work, they evolve to solve these different problems. They have very different constraints than what are relevant to us. And so I think that the thing that's valuable in biology is not the living systems themselves, usually. The thing that's valuable in biology are the nanoscale machines that make up the living systems, the machinery at the core of the system, not the actual full living system itself. And so I would love to call us a nanotechnology company, but that term has been ruthlessly abused to the point where it really doesn't mean anything anymore. So I'm still looking for the right term. I mean, yes, we are technically a material science and mining company. I'd love to define us as the first true nanotechnology company because we actually build nanoscale machinery, and unlike everyone else in this space that just makes chips, which again, that's hard. I'm not trying to, that is a very impressive. We took sand and made it think. Like, that's clearly very impressive. But yeah, I'd love to reclaim the term nanotechnology, I think is where I'm landing on this one day.
I want to go into that explanation one more time. You use this term a lot, and I think I probably get it because I've listened to you, read, and thought about it, but you keep saying machine in reference to kind of a biological construct of sorts. Tell us what that machine looks like. How do what does that mean to you? It's
pretty amazing. It's absolutely incredible. And it's an excellent question. So when we think about machine at the macro scale, like at the scale that you and I exist at, we're talking about like the pistons in your car or your washing machine. And, you could take it apart and you could figure out how it works, right? Pretty quickly in most of these machines. When you look at the nanoscale, all these proteins, like the enzymes that break down the food that you eat or build up your body or modify your DNA or the proteins that detect light in your eyes, all these things, they tend to be mechanical in some aspect. Like, they respond to the environment and they move and they do something, and then that leads to something else happening. So they're mechanical, but they don't look anything like macro scale machinery. They look like blobs. Right. They're literally blobs that kind of blobify into a different way, depending on an input. And they do it repeatably and reliably and mechanically, but they look totally different. A good mental image I can give you is like on our mining program, for example. These things you could imagine as little rings. The machines look like little rings, and they're just floating around. And they're kind of relaxed and loose and vaguely blobby until they bump into a lithium atom. And then the machine snaps shut. It literally looks like a mousetrap and just traps the lithium atom or multiple lithium atoms. And then we're able to pull it out, remove the lithium, and then put it back into the system and say, grab another lithium atom for us. That's really what these things are. And the advantage of that, well, there's quite a few advantages, but one of the main advantages of that is because it's a machine, it's predictable and it's repeatable. That's the big problem with using full living systems, because even the simplest bacteria you can think of is made of 10,000 to 100,000 different types of those machines, all operating together,
complex
millions
systems.
of copies of them. Yeah, you don't know what most of the things are doing. And the thing you want it to do is one tiny fraction of all the things it's doing. It's over complexifying the problem. Just take the machines and engineer the machines to do what you want. They're not alive. They're not going to escape and reproduce in the wild or anything like that. They'll break at some point, and then you just put in new machines.
Yeah, I love that explanation. Last kind of industry question, but we talked about kind of that 20, 30-year horizon. And, for a lot of folks in the investment space, it's synonymous with the idea of deep tech. Right. It's kind of this longitudinal, very complex, very investment forward, but astronomically high payoff. So I'm curious for your perspective on deep tech, how you think about it, how you define it, how you look at it, just how it's different than like what most people know in the startup world. Because I think most people probably would put you into a deep tech category. Yeah, give us a sense of that.
So, deep tech, the way it's typically defined is it is some really, really complex product that you're developing. Usually there's a hardware component to it. And it's something where it can sound like science fiction. It's going to take a long time to generate revenue, but the potential is huge. Now, what's interesting, and I've kind of thought about this a lot over the last couple of years, I actually think that there's something somewhat perverse about that perception that serves to the disadvantage of deep tech founders. I think that people say so often that deep tech takes a long time to generate revenue that people assume that that's just what it should be. And I actually don't know that that's really the case. Now, for sure, things like, I think Sam Altman at one point at YC, he was always like, just sell, sell, sell. and then, build the bigger thing later. And then obviously OpenAI dropped $1 billion and then started selling, right? So like, obviously there's exceptions to what I'm about to say. Like sometimes you can't sell until you spend $1 billion. But I even think in the course of Aether, I could have done better in the early on time of finding people to surround myself with and finding markets where I could sell faster, even if they weren't the most valuable markets to begin with, just to start getting that experience of developing a product. And I think that when you think about deep tech, there's just this incentive sometimes, especially when the capital markets are frothy and people are just writing checks to whatever idea, to just build the coolest tech. And again, that could work. There's examples of that having worked well before. But I think that there's sometimes a discipline that's lacking and even an expectation that's lacking of like, hey, build the really cool tech. But what's the plan to generate revenue 4 years from now or 2 years from now? And it will still take longer. The expectation should not be that it's like a SaaS company or an app. It's not going to be that fast. But I do think that things could be faster than what most people expect in the space as well.
Yeah. Okay. So let's dig in on kind of the heart behind Aether. So I glossed over it to get to the exciting part of the product, but I really think that what you've built and the why behind it is so powerful. So let's get back to the why. You talk about this concept of scarcity and seeing it as you were raised back and forth, and then seeing abundance here, scarcity there, back and forth and back and forth. How was that part of your vision as you started to think about building a company? Like, where did that fit in to that aha moment of Aether?
I want to see a future with tens of billions of human beings united in some future political system with no war that I might not live to see, but I would like to do everything I can to start the wheel turning in that direction. Yeah. And one thing that was very clear to me, living in the US versus living outside the United States, is that I don't want to say consumption is a human right because that's weird. But I do think that everyone wants to provide a better life to their children than they had.
Yeah.
And that inherently means greater consumption. It means having a better house, having a car, whatever, all these things that we take for granted here. Everyone else on the planet wants that for their children, and they deserve that. We can't tell them no. That's ridiculous. There's billions of human beings that deserve lives as happy and as fulfilling, as rich as ours, at least from a consumption perspective. And so the thing that kind of dovetailed to Aether was, okay, if we could have tens of billions of human beings on the planet, how do we, as rapidly as possible, industrialize and grow the manufacturing base of our species so that it's not only possible to do that, but it's economically advantageous to do that? So like a good example I can give you is in the pharma space. It's totally unacceptable that HIV is still a problem in sub-Saharan Africa. And it's a problem in part because there's a lot of corruption, political issues, and all that kind of stuff. But it's also a problem because there's no economic justification today to build a $500 million pharmaceutical plant in the middle of the Congo to sell abacavir, a known drug that would prevent HIV transmission and help these people live normal lives, at 10 cents a day or whatever they can afford. It's just That math doesn't work. But what if the plant costs $5 million instead of $500 million, right? Okay, well now this could actually make sense. The capital intensity is dramatically lower. We could actually think about building a pharmaceutical base in Africa so that things like HIV just go away and we just eliminate that scourge from our species forever. And there's so many other examples like that of if we could just make it cheaper and faster and easier, and ideally also greener. That's important. We'd like to preserve the planet we live on in an ideal scenario. But if we could make it cheaper and faster and more efficient to manufacture a lot of these things, I think there's a lot of run-on effects in terms of improvement to society that would manifest from that. And that really was kind of, then how do you do that? Well, nanotechnology. Well, how do you build nanotechnology? Well, okay, synthetic biology seems like the path to build nanotechnology. So then Aether comes out of that. That's kind of the path that leads to Aether.
You use some terms that I love around the capacity to build, to scale, to do it cheaply, to do it reliably, to do it universally, that are core to the future of abundance. So give us that kind of that horizon. Like, what are the kind of the pillars that you look at as part of that?
Yeah, so I think there's sort of three core capabilities in order to build this future of abundance. The first is you need to be able to just rearrange atoms. And the technical term for that would be you need to be able to catalyze any chemical reaction you want very quickly. So you want the design of molecules to not be a PhD in chemistry. You want it to be someone moving Tinker Toys around on a screen and saying, this is the new arrangement I need. And then a machine just makes it for them, right? And you want that to be as complete and total as possible. So total molecular prototyping is the first one. So that's where our materials program comes into play. It's the genesis of the first one. How do we get really good at catalyzing chemical reactions, moving stuff around? The second one is you need to be able to grab on to arrangements of atoms and pull them where you need to go. You need to move them around in some situations because you can almost imagine an assembly line, right? You're going to need to actually move these things to build more complex structures. Our mining program is the second one. How do we get really good at grabbing things and pulling them into a different environment, into a different compartment, into a different reactor, whatever that is? Right now we're pulling metals, but it's just grabbing atoms, right? It doesn't have to be a metallic atom. It could be something else. The third capability is, how do you stitch these two together from a process engineering perspective so that you can build shipping container-sized manufacturing systems that are as modular as possible so that you go to that idea of your pharmaceutical plant does not cost $500 million. It costs $5 million because it's 5 shipping containers that are stitched together with pipes connecting them like Lego blocks almost. And the inputs are super cheap, available resources there, like maybe there's a petrochemical input, a sugar input, and something else, like whatever's cheap in that area. And the output is a Baclovir. And then it gets pressed into pills, right? Pressing pills is not the problem. It's usually synthesizing the drug. That's the problem. So that's kind of how I see the capabilities of the company developing. And that goes back to that idea of not putting the cart before the horse. Find the high value applications in each one of these areas where it makes sense to invest now to see that return. Don't over-engineer it for the future, but make sure you're pushing in the right direction. Like, for example, the capability in the third bucket of these modular shipping container-sized systems, the way we're going to be developing that over the next 2 years is actually in our lithium mining application. Because what we've discovered is that an advantage of our technology, if it works the way we think it will at scale, which, always an open question. That's kind of why you have to find out. An advantage of the modular approach is not just that our OpEx, or our cost per kilo of lithium is going to be lower, but our CapEx is going to be dramatically lower. I mean, it's going to be crazy. So you can sort of almost imagine a future where there are these massive factories where on one side the input is protein and sheet metal, and the output on the other side are shipping container-sized manufacturing systems. And they're just deployed anywhere on the planet, hooked up to solar power, and boom, they're rearranging atoms and making products.
You talk about this, but there is this kind of reality around if we move asymptotically towards consumption for everyone, we need to do so in a way that has a correspondingly decrease in extractive,
damage
methods. Yeah, damage.
Yeah.
How do you balance that? A lot of these products that you're envisioning and thinking about and building are actually part of the solution too. So clearly you are thinking about it, but I want to just kind of hear you talk through the way you balance or think about that kind of tension or juxtaposition.
Yeah, totally. So I mean, I have a couple thoughts here and a metaphor that I'm particularly proud of, but you'll tell me if you like the metaphor. The first thing I want to say is that something that I think the industry has learned the hard way a few times is that it is not good enough to just be green. At the end of the day, someone buying a straw, it doesn't care necessarily that it's compostable. They just care that there's a straw. And in fact, many people complain now that we have paper straws and stuff like that. So you ideally want to be green, but you have to provide some new value. That's the minimum you have to play at. But the metaphor that I'll use, and the reason why this sort of nanoscale catalytic assembly of products is almost always going to be greener than our traditional way of manufacturing things, is because of the way we traditionally do chemical manufacturing. So atoms will form bonds with each other only at a certain angle and at a certain amount of energy when they hit each other. That's how all chemistry, that's how every piece of matter works. What we have done as a species very well over the last 300 to 400 years is we have gotten really good at kind of hacking the statistics of how often atoms hit each other to make really complex products. So like you can imagine, why do we use so much energy when we're doing chemical manufacturing? Well, a lot of the time it's because, these two atoms will only bind if they're at this angle. And because we can't grab them individually and put them together, we're just going to shake this thing so hard. We're going to heat up. We're going to shake it so much that it's just going to happen enough for us.
Yep.
That's super inefficient. It's almost like, if I kind of take the extreme analogy here, imagine you bought a Lego set and the way you put together a Lego set is you shake the box until it comes together correctly. Like, is that theoretically possible? Yeah. Is that going to happen in any reasonable amount of shaking? No. So the advantage of this approach where you have little machines, little proteins that grab onto atoms and put them together correctly is it's just so much more efficient. It makes sense. It's how you would do it at the macro scale, just put it at the nano scale. So there is this inherent sort of environmental friendliness to all this manufacturing processes simply because the efficiencies are, in many cases, many orders of magnitude greater than anything you could have in traditional manufacturing. But I do think it's important to kind of break down to first principles what are the real environmental benefits of the technology versus imagined environmental benefits of technology. Break it into first principles. Most carbon emissions come from the power to pump liquids. You're not going to fix that problem. It's a law of physics. You still have to pump liquids. And the transport cost of just moving stuff around. The thing that's going to solve carbon emissions is not synthetic biology. The thing that's going to solve carbon emissions is electrification. It's solar and it's batteries. That's what's going to solve it. And it's already well on its way to solving it. So you got to really understand what are the benefits of the tech before you go out and make some of these claims.
Sure. I mean, one of your first applications is, as we talked about, is lithium extraction. And that's kind of one of those places where we hear a lot about the balance between electrification and knowing that we need to do it and knowing we need lithium to do it. And how do we do it responsibly and best for the earth and whatnot. So I'm curious kind of how you think about your opportunity to make a major impact in a critical part of the move toward a more sustainable future, which is doing lithium mining better, smarter, more efficiently, like you kind of just lay out. Talk to us a little bit about that lithium mining ongoing discussion that we all kind of hear about.
Yeah. So, I mean, I think the real benefit of this approach to lithium mining is it takes deposits of lithium that exist underground in water deposits. And all you're doing is you're pumping the water out, you pass it through our system, the lithium stays in the system, and you pump the water back down. So it's as non-invasive as you can imagine, right? It's literally just there's no more lithium in the water. And lithium isn't biologically relevant for most situations. So whatever microbes live down there will be totally fine. That or someone's getting a Nobel Prize for discovering a new class of microbe. So I think that there's a lot of advantages to the approach we have. And, you know, a lot of direct lithium extraction technologies talk about this potential benefit. A lot of them don't really have that benefit because they're not that efficient extracting lithium. They use up a lot of energy. A lot of them need a ton of acid, like basically hydrochloric acid, for their technology to work. And so that just becomes its own problem. But this is generally the idea is instead of strip mining the earth and creating these huge pits in the ground, you're sort of in an almost passive way pulling lithium out of the ground. But what I will say is, you know, I do think when I think about the trade-offs myself personally, I do think that sometimes you will have to sacrifice some strip mining in one area. I'm not saying for us, but just as a species, to save the rest of the planet. So I think what we should be focused on as a species right now is taking the absolutely disastrous idea of pulling oil out of the ground and burning it. And how do we stop that as quickly as humanly possible? And I actually, another point of view that I have that a lot of people here in Silicon Valley don't like, is I actually don't think it's a bad thing to pull oil out of the ground, right? Oil is this incredible resource of super high energy carbon that we can turn to a bunch of different things. The problem is when it leaks and or when we burn it. That's the big problem. So if we could just keep taking it out and not burn it, that's amazing. We're not destroying the environment then. We're just building really complex products out of it. And it's super useful. Just stop burning it, for Christ's sake.
I mean, you're seeing cool stuff. You're at the forefront of some of the most interesting stuff happening in science, technology, and engineering. What are the big innovations and fields of research in climate tech, in sustainability, or that you see it with potential in those places that are most exciting to you outside of what you guys are doing? Who else are you looking at? What else are you seeing technologically? That you're like, okay, this has huge potential down the road too.
Yeah, I mean, I would say that one of the companies I've been most impressed with, and they're not really a competitor of ours. We exist in different kind of operating space, but I'm just very impressed with what they've been able to do is Solugen. They operate in the oxidative chemistry space, so like peroxides and stuff like that. They've just done an excellent job. So I think they're impressed by what they've done. When I think about what's really going to change things, the companies that I get the most excited about are the companies that have a unique way of generating data for a very practical problem, and they can feed that into machine learning. Like I'll give you another example. There's a company, Mitrachem. They develop new classes of batteries. Very, very smart people running it. Really cool, exciting technology. What they've developed is when you do traditional battery development, you basically need to spend a crazy long period of time running the battery over and over and over again to figure out what its lifespan is, right? If a laptop battery is supposed to last 4 years, well, you might have to charge and recharge it for over a year before you find out, does that design have good lifespan or not?
Right.
What Mitras has figured out is a very high throughput, fast way of testing them in a much shorter amount of time. So they can generate these data sets in weeks that people would take years to generate, and then they can feed that to machine learning. And they've made some really incredible progress with entirely new classes of batteries. And that to me is a really exciting idea because we sort of assume that battery energy density is approaching a limit, or that we know what the limit is today. But also 10 years ago, we thought that solar would be like 50 times more expensive today than it actually is.
Right.
It just turns out that if you can find a way to have fast learning cycles and really start to generate that data, whether it's machine learning or not, you can just make leaps and bounds that are much faster than what anyone else can expect. So those are the kind of companies I get excited about. I think if you're just doing machine learning off existing data, that's hard because existing data usually isn't enough. It usually kind of sucks from a quality perspective. But if you've found a really cool way to generate data for a problem that has real practical implications, there's a good chance you're going to become a pretty big company.
Yeah. So let's end, with something that I think will give folks a lot of hope. Like when you think about what inspired you to create this, when you think about the objectives you have, when you think about what you want your legacy to look like, describe the world that you think we could build 20, 30, 40 years from now.
So I think if you look at the world over the next 40 years, sort of three areas, one of them being us, but there's sort of three things that I think will change fundamentally and make the world a much better place and the human race much better. So the first is, I think we are seeing just the inevitable tsunami of electrification. We are seeing solar rapidly become, in many places in the world, the cheapest form of energy to install and to operate. I think there's a global report from some UN agency that said that we're probably going to see peak CO2 emissions in the next 5 years. And we're going to start to see that reverse very quickly. So I think there's still going to be a lot of problems with climate, but I think we are seeing the light at the end of the tunnel on the climate change world. And there's going to be a little bit more warming, but then it's going to start to go back. So that's the first thing. I think electrification is a steamroller, and the work that many companies are doing, from what Elon Musk started with Tesla to all the other people developing new types of solar panels, that train has left the station and it's well on its way. That's the first thing. I think the second thing is that I can't tell you how excited I am about the GLP-1 drug Ozempic, because I think what it's telling us, I don't know if you've been following this, but they're basically throwing it at whatever disease they want and it just fixes the disease. And I think that the reason why I'm excited about it is twofold. One, I'm excited fundamentally because it kind of seems like we found a therapeutic that just is a shotgun that just blows away diseases. And there might be, who knows, right? We thought amphetamines were great until we found out that there was a real big problem with amphetamines. So I will fully admit that 5 years from now, I could be, totally wrong about this. But the reason why I'm excited about that is not just about the GLP-1 drugs themselves, but it's because I think it is opening up in the public conversation this idea that we are able to modify our bodies to become dramatically healthier in a way that goes beyond typical pharmaceutical intervention, right? You can start to imagine people that just take this drug because it lowers the chances of kidney disease. You're just going to be healthier long term. Yeah. So it's the second sphere that I see or thing that's happening that I'm very excited about. I think we're seeing real applications of human augmentation that are pharmaceutical for now. And I think will continue to grow to the point where, I am very excited for a future 40 years from now where my children live with dramatically longer lifespans and diseases that you and I have to deal with just don't exist anymore. So that's the second thing. I think human health and human augmentation, we're starting to see the beginnings of that, I think. And GLP-1 is kind of the thing that's catalyzing that to some extent, because hot damn, that thing just seems to work on everything. And then for Aether specifically, the impact I want us to have in the future is I want us 40 years from now or 20 years from now to be in a world where the planet is covered in these shipping container-sized manufacturing systems. Everything from high-performance materials to pharmaceuticals to metals to anything else are incredibly cheap and easy to manufacture everywhere on the planet. You can see the average GDP per capita of the planet rapidly skyrocket, even in the most abject poverty-laden areas, because there is an economic incentive to invest in those areas because the cost to do so is so low, and to industrialize those areas. So hopefully we'll see all three develop the way that I just described. But, even if they develop partially, I think it's going to be an incredibly bright future. The golden age of humankind is probably starting relatively soon.
That's a pretty amazing and optimistic vision. I love it. Big thanks to Pavle for joining us on the podcast today. I am completely in awe of the scale of his ambition, and I am so inspired by his vision of an abundant future. Often we hear tech founders say they want to change the world, and that ends up meaning a faster smartphone or a more convenient way to call a cab. Those are great things, and they make a nice life. But how many folks are actually out there working on technologies that, if they prove out at scale, could end resource scarcity? How many founders position their company as a solution to end human conflict? It's a long road for any deep tech startup, and there's lots of ifs along the way. But I'll be eagerly following Aether's work because it's a beautiful vision of the future, and I, for one, want to see it come true. If you'd also like to learn more about Aether and their technology, you can visit their website at aetherbio.com, or you can find them on social media at AetherBio on LinkedIn or at Aether Machines on X. And you can connect with Pavle on LinkedIn at PavleJeremic. We'll have all those links for you in the show notes. For any questions, comments, or ideas sparked by today's conversation, or if you have any great ideas for future conversations, you can email us at cic@consensus-digital.com. That's cic@consensus-digital.com. Or you can also connect with me directly on LinkedIn or Threads at CKGONE. As always, if you like the show, please give us a follow, a like, or leave a review wherever you listen. It's really the best way you can help us grow our reach and continue bringing you more awesome conversations with business leaders that you want to hear from. Thanks, everyone. We'll see you next week with a brand new conversation. Consensus in Conversation is hosted and executive produced by me, Conor Gaughan. The episode was produced by Will Gatchell and Jeff Rock with editing from the good folks at Reasonable Volume. Special thanks to the Consensus team, including creative director Kate Tucker, Greg Hergel on research, and Patrick Gallagher on strategy. Consensus in Conversation can be found on Apple Podcasts, Spotify, YouTube, or wherever you listen. Consensus in Conversation is a podcast by Consensus Digital Media, produced in association with Reasonable Volume.